Okay, hi everyone. So, I'm not going to read too much into my impression that you were all wildly unenthused about what I talked about in class today. But I do think it's pretty cool. I mean, this is kind of one of those things where um, if you wonder, like, what's the big deal? I don't know. I mean, I guess it's not that big of a deal in that 2 plus 3 equals 5, I guess, is not going to be like, party worthy. But there's something pretty neat about the fact that when you have a homogeneous linear system here, and a quick scan will tell you that in this particular case, there are going to be infinite solutions, okay? Um, any point on the line of intersection of these two planes, I'll say that again, any point on the line of intersection of these two planes represents a solution, okay? And each solution, if written as a vector, will be perpendicular to both the vector 1, 3, negative 4 and 2, 6, negative 8. Okay, so I'm just going to work this out here with you all. And when we talk about, looking at a linear system, and specifically a linear system represented as a matrix equation, what we're saying here is that these can be thought of as vectors, these being the matrices, and there's a certain relationship between the vectors R1, R2, and the solution, okay? So here's what we're going to do. We're going to go ahead and solve, okay? I'm going to solve this. And once I solve this linear system for what is likely going to be a parameterized solution, because there are infinite solutions, I'm going to go back and show that that solution is, in fact, perpendicular to both vector R1 and R2, okay? So I'm going to go ahead and start solving. And I'm going to solve, I'm actually going to force you all to do this. I'm going to solve this by way of row echelon, okay? Let's go ahead and solve this and try and get 1 here, 0 here, 1 here, 0 above, okay? So when I do this, I'm going to do negative negative 2R1 plus R2, give me a new R2. I wonder how smooth you all feel doing this. I don't know. I also wonder what time it is again. But anyway, 0, oh no, 0, negative 2R2, oh weird. So anyway, if you're wondering, I just pulled this from your textbook. This is just question number 18. I was just going to give you homework and just say, they were unenthused. They're probably going to be unenthused about homework. But I figured, you know what? Maybe you were just tired. And maybe when you sit on it tonight, you'll be more enthused. I don't know. I just pulled this question from your homework and I'll just take it off your homework, okay? So here I am doing number 18. And when I solve this, I find, whoa, this is what happens. That's very cool. So what this tells me is 1x1 plus 3x2 minus 4x3 equals 0, or x1 equals negative 3x2 plus 4x3, okay? If we want to parameterize, we can say, let's let x2 equal t. I'm going to let x3 equals u, okay? And that tells me then my solution is x1 equals negative 3 t plus 4u, x2 equals t, and x3 equals u. All right, so everything is confirmed here. I do, in fact, have infinite solutions. This is a 2-parameter infinite solution case. And let's go ahead and check that, in fact, that any value of t and u that I sub in here, right? I can let t be a number, let u be a number. x1 will have a component. Any vector represented by x1, x2, x3 So this is my solution as expressed as a vector. Okay, let's show that that solution dotted with either R1 or R2 is going to equal 0. Let's see. R1 is 1, 3, negative 4. You ready? So let's do this first. 1, 3, negative 4, dotted with vector x, negative 3t plus 4u, comma t, comma u. When I dot these, I get, let's see, negative 3t plus 4u plus 3t minus 4u. What happens? Yes, it equals 0. Ding, ding, ding. And you can also, why don't you do the check? You show this one. Show that vector R2 dotted with x also equals 0. Okay, so that was it today. I mean, I like this. It's just yet another window through which you can look at linear systems. I mean, if you really think about linear algebra really is the study of all of the properties of linear systems. And we can look at them, linear systems, that is, we can look at them geometrically, think about lines intersecting, think about planes intersecting. That perspective, though, the physical geometric representation, starts to fall apart as we enter higher space, because we can't conceive of a 6-dimensional space filled with, say, 4 linear equations in 6 space. Okay, that's hard for us. The other thing so there's the geometric perspective of linear systems. We looked at the matrix perspective of linear systems. And when you look at the matrix perspective, what we find is a very algorithmic, programmable way to solve a system by way of row echelon form, right? We then merge our knowledge of matrices and the matrix representation with ideas of orthogonality. And hang on, someone just knocked on my door. Hold on a second. And vectors. And now we're kind of at a place where all these kind of seemingly disparate ideas are coming together. Okay, so that is it. And I don't know, if you're still kind of lukewarm about this, well, I'm sorry. Well, actually, no, I'm not. Maybe sometimes math can be a little bit lukewarm, and you're entitled to your opinion. But I think it's kind of neat. Okay, so homework tonight, very light. Tomorrow I'm going to talk about vector equations of planes. I also have to go over homework from 2 nights ago, don't I? I think I do. So I'll make sure I do that. Let me put your homework up. Okay, that's it. Very short homework because I didn't really get through the entirety of what I wanted to talk about, and we took time out today to practice 3 little proofs. So very light homework. Tomorrow I will finish discussing this section. We'll go over homeworks from this homework and the night before, and then we'll move onward and upward. Bye, everyone.